Okay, so today we're going to talk about 1.9, which is inverse functions. I apologize, this is missing an H here. So the question to start out with is, are each of these functions y or y not? Oh, there's not even the rest of the sentence there. I apologize. Are each of these functions, and are they or are they not? So go ahead and press pause, see what you think, and then come back. This first one would actually be a circle. I don't know how many of you recognize that, but because I have an x squared and a y squared, this would be a circle, which means that it's not a function. The second function, notice each x value has exactly one y value, so this would be a function. And then for the third one, the issue there is when x is 1, y could either be 2 or 5, which means that this would not be a function. There is not a situation where I have one x, each x has only one y. And then for this last one, let's think about that vertical line test. This looks like it goes pretty straight up and down, but it continues to go out whether you realize it or not. So notice that if I were to take that vertical line and scan it across my graph, there would actually be no point where my vertical line is hitting this graph twice, so this is a function. Okay, so inverse functions, they basically undo each other. So for example, if you had f of x is equal to 4 or x plus 4, f of x or x f prime is how we'd oftentimes describe this, okay? F inverse of x is equal to x minus 4. So these two things would be inverses of each other. If I were to combine them and do f of f inverse of x, the plus 4 would actually undo the minus 4. Okay, we're going to talk more about this idea in just a moment. Okay, so to find the inverse of each of the functions, I would have the first one is f of x is equal to x cubed. For right now, I want you to just think about what undoes f cubed or x cubed. So what I want to look at is I would say, okay, well, if I were to take the cube root of that, it would be undone. So the inverse, f inverse of x, is equal to essentially the cube root of x. It's the opposite, okay? Over here, if I have f of x is equal to 2x, f inverse, we denote that with that negative first power, f inverse of x would be equal to, well, here I'm multiplying by 2x, or by 2, so I would divide by 2. Those would undo each other. Okay, now there's something else that's kind of interesting and fascinating about graphs of inverse functions. And so I just kind of want to bring that up, and then we will look at this a little bit more with some examples. But the graphs of inverse functions are really special. So I'm going to try and freehand this because I can't use straight lines, so I apologize. For this first graph, f of x equals x cubed. If you recall, this graph, the parent function looked something like this. It's kind of that S-shaped one. Okay. Well, here's the cool thing. F inverse of x, the cube root of x, and I don't expect for you to know what this graph actually looks like, but the cube root of x actually goes through those same 3 points, only it looks something more like this. Okay, now why is this so special? Well, the inverse of a graph and itself, or the inverse of an equation, will always reflect over the line y equals x. Okay, so our graphs will always reflect over this line y equals x. Okay, over here, I can show that to you with this graph too. Again, freehanding, so it's not going to be perfect. If I have f of x is equal to 2x, so that first function, my y-intercept would be 0 and my slope would be 2. So I'd go up 2 over 1 or down 2 over negative 1 and there's my graph. Okay, my second one, my inverse, this one was the red one, my inverse would be essentially 1/2 x, right? So x divided by 2 would be 1/2 x. So still 0, 0, and this time I'm going to go up 1 over 2, or down 1 over 2. Okay, so this graph would look like this. Okay, now let's look at the line y equals x, and this won't be perfect because it's not done on graph paper. But notice how my two graphs actually reflect across that line. Okay, so the actual definition of an inverse function is, and this is what I kind of alluded to at the beginning, is f of g of x is equal to g of f of x, which is equal to x for all x values in the domain. So to verify an inverse algebraically, what we have to do is we have to find f of g of x and g of f of x. Okay, you need to find both because that's how the definition is actually written, is it has both pieces to it. So the question here is, are these two functions inverses of each other? So what we're going to do is we're going to figure out those two pieces. We're going to have f of g of x, and then we're going to have g of f of x. If both of those equal x, then yes, we have inverses. If one of them doesn't though, they are not inverses of each other. So let's check this out. F of g of x. So this would be f of g of x, which is 7x plus 4. So I would have 7x plus 4, that's my g of x, minus 4 divided by 7. Notice that I just replaced this 7x plus 4 with x. Okay, so now simplifying this, I would end up with 7x over 7, which is equal to x. Okay, so that's a good sign for that first one. Let's check out the second one. I'd have g of f of x. So if I plug in g of x minus 4 over 7, I'm going to replace x with x minus 4 over 7. So this would be 7 times x minus 4 over 7 plus 4. Or the 7s would cancel out and I'd have just left x minus 4 plus 4, which is equal to just x. So because both of these compositions of these functions ended up simplifying to just x, we'd say yes, these two functions are inverses of each other. To verify an inverse function graphically, you would use the horizontal line test. Now, to be clear, every function has an inverse. Everything has an inverse. The question here is whether or not the inverse is a function or not, okay? So that's kind of what this horizontal line test is testing. Is it saying, is the inverse a function? Okay, so I might ask you the question, does this have an inverse function? Okay, and your answer would be either be yes or no based on the horizontal line test. If I were to ask you just, does this have an inverse? Your answer should always be yes, because we can always find an inverse to anything. It just may not be a function. Okay, so with a horizontal line test, it's very similar to the vertical line test. You're just going to take an imaginary horizontal line and pass it through your graph. Okay, slide it kind of across. And does that imaginary line touch the graph in more than one location? Notice down here at the bottom it doesn't, but then up here, and even depending on how straight you draw your top line, up there, all of those locations have the graph touching at multiple locations. So in this case, this would not be an inverse function, or the inverse would not be a function. Okay, so a little vocabulary. A function, if a function has an inverse, it's considered to be 1-to-1. If each output has exactly one input. So each output has exactly one input, each input has exactly one output. That means that if you have a function and a function inverse, then it would be considered to be 1-to-1. That won't really come up much until you get into calculus, in which case you might use that language a little bit more. You might see that language a little bit more. But for now, I just want you to be aware of kind of what it means. Okay, so we can graph this, or we can find the inverse graphically to different things, similar to how I did on one of those first slides where I was showing you the graphs with it. But essentially, all that we're going to do to graph the inverse is that we're going to switch the x and the y coordinates. Okay, so what we're going to look at is we'd say, okay, well, here's a point that we know. This was the point 0, 0. Okay, here's a point that we can tell that would be the point over 2 up 4. And then here's a point that we know that would be over 2, 4, 6, 7, up 2, 4, 6, 7. Okay, so for my f of x, or for my initial function, just so you can see this in a table, I'd have the points 0, 0, I'd have the points 2, 4, and I'd also have the point 7, 7. So if I wanted to graph the inverse of this function, f inverse of x, all that I do is I switch the x and the y values. So I'd have x and y for f inverse would now still be 0, 0. I'd have 4, 2, and then 7, 7. Watch what happens when I graph those. Here's 0, 0, over 4 up 2, 7, 7. Notice that my graph is reflecting across that line, y equals x. Okay? To find an inverse function algebraically, what we need to do is we're still going to also switch that x and y. But because of this function notation, we have to do a couple of steps first. So we're thinking about the graph here, and in order to change the graph, all that we did was flip the x and the y values. Excuse me, I just yawned. So what we're going to do is we're going to do the same thing, except for first thing that we want to do is we want to determine whether or not f of x has an inverse function. So think about the graph here. Okay, would this pass the horizontal line test? Yeah, it would. It's a straight line. It's going to pass the horizontal line test. Okay, so then the next step is that we're going to switch f of x with y. This is just for notation purposes to kind of help us out. So we're going to say, okay, y is equal to 2x minus 5. And now we're going to switch the x and the y. So I'd have x is equal to 2y minus 5. Now, I want to be really clear. At this step, this is no longer my original function. It's no longer f of x. Instead, this is now the inverse. As soon as you switch the x and the y, that becomes the inverse. Now, we always want our equations to be in y equals form. So we're going to go ahead and solve for y. So I'd have x minus 5 is equal to 2y, or y is equal to 1/2 x minus 5 halves. You could have written that as x minus 5 over 2 as well. That would have been just fine. Okay. Now, this is written as y, and these can be very confusing because which one's the inverse and which one's not the inverse? I don't know what's happening. So what we want to do is we want to go back and replace this y value with f inverse of x. All right. And then we want to verify the inverses. So how we verify the inverses is go ahead and just plug them or figure out that f of g, I guess in this case it'd be f inverse of x. Okay, and then also f inverse of f of x. And those should work out so that they both equal x. So if I were to do this one really quickly, f inverse, if I plug that into my equation, I'd have 2 times x minus 5 over 2 minus 5, which would be x. Oh, you know what I'm realizing? I made a mistake. I apologize. This would be x minus 5, and this is why I noticed that maybe I made a mistake somewhere, is that I'm like, ooh, that doesn't equal x, and I know it probably should. When I added 5 over to the left-hand side, I did not actually add it. So here, I'll circle these so that you can see them. All of those should actually be positive, right? Because I'm adding 5 to both sides. So this would become plus 5, plus 5, plus 5, which makes this over here plus 5 and plus 5, and that is equal to x. Okay, so this is why it's really good to verify, because I wouldn't have caught that had I not. So you all probably saw it as I did it, so I apologize if that confused you. Now, for f of x, if I plug in f of x into f inverse of x, I'd have 1/2 times 2x minus 5 plus 5/2. And if I simplify this, this would be x minus 5/2 plus 5/2, which is just equal to x. Okay, so that verification step is really important, not only to double check to make sure that it actually works, but then also to verify your work. All right, so this one, I want you to find the inverse function, okay? And then I also want you to verify this one, okay? So the verification step I actually think takes the longest out of everything, but I want you to find the inverse and verify. Go ahead and press pause, try it, and then come on back when you're ready. Okay, so my first step here is going to be to change this over to y. So I'd have y is equal to 5 minus 3x divided by x plus 2. And then I'm going to go ahead and flip-flop my x's and my y's. So I would have x is equal to 5 minus 3y over y plus 2. Now, part of the reason why I gave you guys this one is because this is a little weird of how to solve for y in this case with there being multiple y's. So what I'm going to do is I'm going to go ahead and multiply both sides by y plus 2. Okay, so I would end up with xy plus 2x is equal to 5 minus 3y. And now let's get all of the y's over to one side and then everything else over to the other side. So I'm going to add 3y to both sides, xy plus 3y, and I'm going to subtract the 2x equals negative 2x plus 5. Okay, now the reason for doing this is now that I have the y's on one side, I can actually factor out a y. So I'd have y times x plus 3 is equal to negative 2x plus 5. And now I can divide both sides by x plus 3. And I have my inverse. So f inverse of x would be equal to negative 2x plus 5 divided by x plus 3. Okay, now for verification purposes, we need to actually test this out. Let's see if it works. And this is going to be a lot for us to plug in. So if we do f of f inverse of x, we would have f of this stuff. So everywhere that I see x, I'm going to plug in all of that stuff. So I'd have 5 minus 3 times negative 2x plus 5 divided by x plus 3. Divided by, I would have negative 2x plus 5 over x plus 3 plus 2. Now, warning from last chapter, if you recall, when we had a fraction inside of a fraction, we called these complex fractions. So we had to make common denominators for both the numerator and the denominator separately. So the numerator here would be 5 minus, I'm going to go ahead and multiply in this 3. So I'd have, actually, it would end up being plus 6x minus 15 over x plus 3. Okay, and for this one, I can multiply this by x plus 3 over x plus 3. So I end up with, 5x plus 15 plus 6x minus 15 over x plus 3. Or this is 11x, I'm just checking my work here, 11x plus 15 minus 15, so that goes away, divided by x plus 3. Okay, great. So then that's my numerator. My denominator would be this, negative 2x plus 5 over x plus 3 plus 2. So I can multiply this one by x plus 3 over x plus 3 to make those common denominators. So this would be negative 2x plus 5. I'm going to multiply that 2 in, so plus 2x plus 6 divided by x plus 3, which if I simplify that, I end up with 11 over x plus 3. Okay, so coming back over here, did my numerator, did my denominator separately, I have 11x over x plus 3 divided by 11 over x plus 3. So if I keep change flip or keep the numerator, make this multiplication, flip the denominator, notice the x plus 3's cancel out and the 11's cancel out. I am left with just x. Whew, that's a lot of work, but that's how you can actually verify this. Now, we should really do f inverse of f of x as well. I actually don't have enough space on this page. Also, I think that you guys get the point that it's important to verify. You need to be able to do both of them though, so just be prepared to do both of them. And if I ask you actually to verify, finding the inverse, you can just do that, and if you verify it, that's great. If I ask you to verify though, you need to show both pieces because that's part of the definition. You need to have the f of f inverse of x and the f inverse of f of x. Don't be lazy and just do one like I'm going to do on this one. Do both if I ask you specifically to verify. Otherwise, I will mark you down for not having it complete. All right, so that is 1.9. Your homework is posted on the assignment sheet on OneNote, so you guys can use the remaining time of class to work on the homework assignment for 1.9. 1.9 will be due tomorrow. Thank you. Have a great day.